Hello, everyone, and I hope that you're doing great today. Now, today we're looking at this CSEC Physics Past paper. It is a paper 2 from the year 2023. It is a May-June paper. As always, please remember to read through the instructions carefully. And if you should have any questions or queries, please clarify those with the examiner before you begin the examination. At this time, let us jump into section A, question number 1, and it reads, Figure 1 shows the setup of an experiment to determine the specific heat capacity of 300 grams of a liquid using an electric heater. The heater has a power rating of 105 wattage. All right, so please make note of the variables that we have here, the mass, which is 300 grams, and the power rating, which is 105 watts. All right, this experiment is shown below here. And notice they have an electric supply right here. And then we have the heater coil at the bottom, and we also have a stirrer. And here we have the thermometer. We have the polystyrene foam lid, and we have the polystyrene foam cup. All right, and so what they give us here is that they give us a chart. And so we have here temperature and time data for the liquid in the polystyrene foam cup are shown in table 1. And so we have temperature and we have time. All right, so there are the values. You can just make a note of them. All right, and first part of the question now asks us to define the term specific heat capacity. And specific heat capacity is the heat required to raise the temperature of a 1 kg substance by 1 degree Celsius. Also, just to note, you can refer the mass in terms of grams and also the temperature in terms of Kelvin, and you will get the marks just the same. All right. Now, for part B, it's assuming that all of the electrical energy produced by the heater is transferred to the liquid, and that P is the electrical power of the heater, T is the time duration for the experiment, and M is the mass of the liquid. C is the specific heat capacity, and we have delta theta, which is the increase in temperature of the liquid. All right. And so just a point to note right here, for us to understand what's going to happen here, we know that energy of the heater is given as power times time, and energy absorbed by the liquid, it is MC theta, delta theta. All right, and so here now is a change of temperature. And so they ask us here now to deduce the formula, which represents the heat energy transferred from the heater to the liquid. And so again, whatever energy is in the heater, which is PT, power times time, is equal to MC, change in temperature. All right, and so that will be our formula right there. All right, for part C, so using the grid provided on page 7, plot a graph of temperature, all right, versus time. And so let's go to that before we come back to this calculation here, just to show you what is happening in the graph. Usually you want to put a title, all right, and then again, what is very important is to ensure that you label your axis. So the y-axis is temperature because that is the dependent variable. And on the y-axis, we have time, which is the independent variable. All right, again, you plot your graph and using fine lines. What I've done right here is to draw a line of best fit, as you know that a few points will be slightly out of the range. All right, so that's the expectation right there. Your line must be fine and straight and also neat. And a zigzag line, you're going to lose marks. Again, while labeling, please put the units as well for each variable. All right, please ensure that you do that. So let's go back to our calculation. And so for part D, so calculate the gradient G of the graph. And so gradient is a change in temperature over the change in time. And we're talking about the change on the y-axis over the change in the x-axis. And so therefore, as a formula, we're going to have T2 minus T1 divided by T2 minus T1. And just to make a note with the difference in T's, the uppercase T represents temperature and the lowercase t represents time. Again, they will not accept rise over run, so please not write that on any physics paper. All right, it's the change of y over the change of x that is acceptable, but do not write rise over run. All right, gradient now is equal to 53.5 based on the triangle that I have there. So I will show you just after this. And then that will minus 30. And then we have 325 minus 50.25 based on my triangle. All right, so That is very important right there. And so when we work this out, we have 0.0855 degrees Celsius per second. And the reason why we have that again is because the y-axis represents temperature and the x-axis represents our time. So therefore, the unit for the gradient here is degrees Celsius per second. All right, and so just to show you my triangle right here, again, just to make a note that the triangle should be large. If you use a very small triangle, you might lose a mark or two. So please be very careful in choosing your triangle for gradient. All right, for part E, it said that given that G is equal to P divided by MC, and just to make a note right here that G is our gradient that we calculated up top, and P is power, and M is mass. And of course, you remember that C is the specific heat capacity as stated right here. All right, and that is of the liquid, of course. And it said express your answer in SI units to one significant figure. And just to make a note as well in the physics examination, please try your very best to use units after every calculation. Please try to do that. That's very important. Sometimes you lose a mark for a certain question, so you do not want to lose any marks at all. So please be very careful. All right. So right here now we have our values for G that we calculated up top. We have power that is given in the statement above as well, which is 105 watts. You should remember that. And 105 watts is the same thing as 105 joules per second. That's the other option for the unit for power. All right, which is energy per time. And then our mass is 300 grams, and we're going to convert that to SI units, so that therefore going to be 0.3 kg. All right, and so we know from this given formula here that if G is equal to P divided by MC, then certainly P is equal to GMC. And so if you should make the specific heat capacity the subject of a formula, then therefore it is equal to P divided by GM. All right, and so we have our power rating there in joules per second. We have our gradient, and then we have here our mass, which is 0.3. And so our final answer will be 4,093.57. And to one significant figure, it is equivalent to 4,000 joules per kg per degrees Celsius. All right, so that will be our answer there for a whopping 6 marks. All right, so please make sure substitute well and apply your formula very well as well. Do not just write answers alone. That's only a mark. Of course, you get the total marks, but please show your working. Very important, just in case you miss something. All right, section 2 of part E is a table 2 shows the specific heat capacities for 3 commonly used liquids. And so we have cooking oil, we have milk, and we have paraffin. And these values are the specific heat capacity for each of them. All right, and so using the answer calculated in E1 and the information in table 2, state the liquid that was most likely used in the experiment. And so this will be milk, and the reason for that is because milk is the closest to 4,000. And of course, there could be a follow-up question. Why didn't you get the exact value? And really and truly because you're doing an experiment. So therefore, you could have the temperature of the environment affecting the reading of a thermometer, or the heat or the energy of the apparatus itself. All right, so there are a number of reasons why we do not get the specific or exact values. And of course, that's why it's very important to do the experiment more than once. All right, and here's the now state one precaution that the class should take in performing this experiment. And one is to avoid parallax while reading the thermometer or any instrument, a matter of fact. And so you must always read at eye level. That is very important. And so that could be one of the reasons why the answers are not exact. Again, you can use a stopwatch to record the time for every second. All right, every 60 seconds, that is, which is a minute. You can prevent heat loss by using styrofoam container or use insulated material to hold the stirrer. So even though the apparatus was a polystyrene, to hold the stirring rod, you can also use something that is very insulated, so no heat is transferred. to the liquid. All right, again, you can stir or slightly shake the container to allow equal heat distribution. That's also important because remember the thermometer may not read the entire liquid immediately, depending on how the heat is traveling through it. Again, you can use insulated sealed around the thermometer and the heater as well to prevent heat loss from the container because remember there are holes in the cover, all right, and so those holes could cause heat to be lost or gained depending on the external conditions. Also, you can ensure that the heater element is covered in the liquid and not touching the container itself because touching the container, then heat will loss the container much quicker depending on the nature of the container versus the liquid. All right, so those are just some suggestions. And of course, any suitable ones will be accepted. All right, for question number 2 is a figure 2. Sorry, this is figure 3 actually. Figure 3 shows a wind turbine used in some Caribbean countries as an alternative energy source. All right, and so there is a wind turbine right there. So part A, so describe how a wind turbine produces electrical energy. And you can actually do it in 2 ways. I have one in blue, one in red. And so let's go with the one in blue, which can explain the one in red as well. It said the wind turns the blades of the turbine, and this is converting wind energy to kinetic energy. So wind into motion. And then the second thing will happen here is that the turning of the blades result in the turning of the generator rotor, and that is producing kinetic energy. All right, you may say kinetic energy. And the third thing that will happen here is that the generator then produces electrical current or electricity, and that is converting kinetic energy into electrical energy. All right, and that will be our 3 marks. All right, so part B is a state 2 advantages and 2 disadvantages of using wind turbines in some Caribbean countries. And so advantages, there are a lot of advantages, especially Caribbean. Of course, it's normally have some great winds for the most part. And so one here is a lower dependency on oil, that's the advantage. Less pollution, and it is renewable as well. So those are many things you could list right there. All right, you have lower electricity cost, of course, cost effective, lower maintenance, reduces imports and costs of energy imports, sustainability or sustainable. It is sustainable. You may have wind is often present, as I mentioned earlier. Generally, in most Caribbean countries, you normally get some good wind. All right, and while using wind turbine, you can still use the land for farming and so on, and also for other development. Of course, even for housing, but of course, you put the wind turbine away from the house. You do not want it too close, just in case you have accidents and electrical shocks and all of those stuff. All right, but yes, disadvantage now. Here we have variation in wind speed because again, you may not have the same consistent wind speed every day. Some day may be very calm and no wind. All right, and again, you may not produce steady current because of inconsistencies in the wind speed. Again, you may have high cost to set up the wind turbines, so installation cost may be very high. That's what number 2 is speaking about right there. And number 3 is a suitable land may not be readily available because again, some Caribbean islands are very mountainous, and to get the wind turbine on hilly sides may be a little bit, or hillsides may be very difficult. All right, and again, depending on where you live, if it is swampy and things like that. So there are a number of factors that can determine suitable land because, of course, the turbine must be fixed firmly and securely to prevent accidents and also disasters. All right, and number 4, now we said may affect organisms that may fly in the path of the blades, of course, for sure, and it can be also noisy. But of course, with modern technology, the noise level will be a little bit lower because they would modify these things to make sure that it is not too noisy. All right, but of course, parts could go bad and then definitely start to make some unnecessary noise. All right, part C is that if the mass of the air that passes through the circular area swept out by the turbine blades every second is 8.5 kg, and its kinetic energy during this time is 2,500 joules. Calculate 1, the speed of the air, and so the kinetic energy, as we know, is equal to half mv squared. And so we want to find v, And so therefore V is equal to square root of the kinetic energy divided by half the mass. And we have a kinetic energy here as 2,500, and the mass here is 8.5 kg, so half of that. And our answer will be 24.25 meters per second. And they also want us to calculate the input power of the air. And so power is equal to energy divided by time. And so therefore we have 2,500 divided by 1. Why do we have 1 here? Because it was in every second. So the time is 1 second. All right. And so therefore we get 2,500 joules per second, or 2.5 kilowatt. All right. Now jumping on to the next part of the question, which is part 3 of the same question. It said the efficiency of the wind turbine, given that the output power of the generator is 1,350 watt. And so therefore efficiency is equal to power output divided by power input multiplied by 100%. And so therefore the efficiency is equal to 1,350 divided by 2,500. And so therefore the efficiency is equal to 54%. All right. All right, next question here, question number 3. It says state 2 properties of electromagnetic waves. And there are a number of different properties that you can list. They are transverse wave, which is one of the first things you want to write, of course. That's generally for all electromagnetic waves. They travel through vacuum. Those are common ones. They travel at the speed of light in vacuum as well. And they can reflect, refract, diffract, and interfere. All right, that's also important as well. And of course, I guess most people will not remember that. But yes, all electromagnetic waves can do that. They obey the wave equation, which is stating that speed equal to frequency times wavelength. And another one here that you can also list is that they can be polarized, especially plane polarized. All right, so once I say they can polarize, you get a mark as well. Now for B, and B is a figure 4, shows a cup and string telephone. And we have a diagram there. So part 1 of this section is said describe how the cup and string telephone works. And so the first thing I want to mention here is that when talking takes place, the bottom of the cup vibrates. So you must mention that the bottom of the cup vibrates. That's very important, because vibration starts in the cup. All right, after speaking, that is. Then the vibration now is transmitted through the string. You must mention that the string must be taut. So if it's too slack or loose, you're not going to get that transfer of vibration through the string. So you must mention that it is taut. All right. 3, the same vibration reaches the second cup, causing it to vibrate. So the second cup will vibrate when the vibration reaches that cup. The vibration then transmits to the air, where it is converted into sound. All right. Or sound impulse, if you want to make specific reference to that. For part 2, is that calculate the wavelength of the sound produced by the cup and string telephone. It's given that the frequency of sound waves in air is 11,000 hertz, and the speed of sound in air is 330 meters per second. All right, so we have the frequency, 11,000, and we have the speed, which is 330. And so just as we remember, the formula for speed is equal to frequency times wavelength. All right, and so they asked us to find the wavelength. And so wavelength is equal to speed divided by frequency. And so therefore it's going to be 330 divided by 11,000, which we get there 0.03 meters. All right, and that's a nice 3 marks. Now for part C, so figure 5 shows a coin at position O in an empty container. An observer is unable to see the coin based on the position of his eye. And so here now we have the coin right here. All right, this is an error. Right? This was placed somewhere else, so you ignore this piece here. All right, I'm not going to delete it. I don't want to cause any disruption in the other notes. All right, so that's hot junction apps for something I type. All right, anyhow, referring to this question, is describe how the observer can see the coin when the container is filled with water. And just to make a point right here, you can actually draw it on the diagram or explain it. But I'll say if you draw it on the diagram, please explain it, because they ask you to describe it, okay? So you have to say something. And so right here we have the water surface. So everything in blue actually put on, well, light. I've also put on the other things in black as well. So let me not say the color because we're going to make a mistake with that. All right, so we have water surface here. And so at the water surface, we have the refracted ray away from the normal. That's very important. If you notice, the ray is refracting away from the normal because remember the difference in optical density. The water will have a higher optical density. The air will be of a lesser optical density. And so therefore moving from a higher to a lower, then the refracted ray will move away from the normal. All right. And so you have this arrow indicating the apparent depth. All right. All right. And so let's now jump into the description. So here it said when water is added when water is added, the following occurs. And I missed out a G right here. So let me just, I'm not going to put it in because when I realize I put in these things, something deletes sometimes. So let me just leave it as it is. All right, for one, here is a light coming from the coin refract away from the normal at the water surface. And 2, the refracted ray enters the eye. And 3, the coin appears to be closer to the surface or it appears to be higher. All right, and that will account for your 2 marks. All right. Now for part 2, it said the refractive index of water is defined as the ratio of the speed of light in air to the speed of light in water. And so this is actually giving us a formula right here. All right. And it said calculate the speed of light in water, given that the speed of light in air is 3 times 10 to the 8 meters per second. And the refractive index of water is 1.3. And so refractive index, even based on the definition right here, it is the ratio of speed of light in air over the speed of light in water. All right. And again, N represents our refractive index. And so refractive index of water is equal to speed of light in air over the speed of light in water. And so based on this, now we're going to have 3 times 10 to the 8 divided by 1.3. All right. And so I want to find the speed of, just to make mention of this. So the speed of light in water, all right, you're going to make the speed of light in water, which is VW, will be the Thermocouple formula. So therefore, it will be VA divided by N, just to make mention of that. I should have put that there as well. All right, so therefore, we have here 3 times 10 to the 8 divided by 1.3. And so what we get here is 230,769,230.80 meters per second, or simply 2.3 times 10 to the 8 meters per second. All right. Let us go to part 3. Part 3 now is to calculate the critical angle of water. And the critical angle, just to make mention here that the refractive index is also given as 1 divided by sine the critical angle. And so therefore we have sine the critical angle is equal to NA over NW. Again, remember for those things up top, which is the refractive index in air and refractive index in water. All right, and so therefore what we're going to have here is that C is equal to the inverse of sine 1 divided by 1.3. And so therefore what we have right here, it is 50.3 degrees. I'll just say 50 degrees, all right, and that is fine. All right, jump into our next question here, question number 4. And for question number 4, part A, 1, it's a draw a label diagram. Well, a label diagram of a structure of a thermocouple thermometer. And this is a basic diagram right here. We have a junction right here. We have a wire type 1 and wire type 2 because there are 2 different wires going to be used. And we have what they call a cold junction where it is connected. And we have our millivolts reading at the end right there. And of course, once you have a difference or change in the millivoltage that is generated based on the heat, then we know that we can convert that in terms of what the temperature is like. All right. Now for part 2, it said the thermocouple thermometer is used to measure the temperature of the blue part of the flame of a small candle. State 3 reasons why a thermocouple thermometer is suitable for this application. Again, just to make note, the first point here, can explain what I was going to say, is that the blue flame is the hottest part. All right, and it is best used for high temperatures. All right, so very important to use thermocouple for high temperatures. It can measure a wide range of temperatures as well compared to regular thermometer. You have a fast response time to the change in temperature as well. It's accurate in measuring temperature ranges, and of course, it's sensitive to small changes in temperature. So those are the basic reasons why thermocouple thermometers are used. All right. And for part B, it's a figure 6 shows a fixed mass of gas, which is trapped in a cylinder by a piston. And it said the gas is at atmospheric pressure, 1 times 10 to the 5 Pascal. It said the volume of the trapped gas is 1.9 times 10 to the minus 4 meters cube. And the initial temperature is 27 degrees Celsius. An electrical heater is used to increase the temperature of the trapped gas to a final temperature of 627 degrees Celsius. So the first thing I want to do is to note these values. All right, so make note of them. This is a diagram showing what is happening here. All right, and it said for part 1, it said use the kinetic theory to explain how the gas exerts pressure on the piston. All right, and so the gas will be here as labeled on the diagram. So we're going to look at why is happening here. So the particles of the gas are in constant random motion. First thing to mention, they constantly collide with each other and the walls of the container. The collision of the particles causes pressure to be exerted. And they said when the particles collide with the container, they exert a force when they change direction. All right, and the force exerted per unit area results in pressure. So pressure is equal to force over area, just to make mention of that. All right, so these points are the outline of how the gas actually exert the pressure onto the piston. All right. All right, so let's now go into the next part of the question here. And this is part 2. It's a calculate the final volume of the gas given that the final pressure is 1.8 times 10 to the 5 Pascal. And with all information given, let me just show you before I actually say it. All of the information given right here, we have our pressure. All right, we have our volume 1, we have our temperature 1, we have our temperature 2, and we want to find our V2, which is our volume 2. Okay, because that's what they wanted to find, our final volume. And so based on this given information, we know that is Charles' law, because if we have temperature, 2 different temperatures, and we have 2 different volume, then for sure we know that pressure is constant, and therefore this is applying to Charles' law, or Charles' law is applied to this question. A point to note also, you need to convert your degrees Celsius into Kelvin, all right? And of course, to move from degrees Celsius into Kelvin, you add 273. So 27 plus 273, you get over 300. And 627 plus 273, we will have here 900 Kelvin. All right, so that's where we'll get these values. All right, and so therefore to find our V2, we're going to have 1.9 times 10 to the minus 4 times 900 divided by 300. And our answer here should be 5.7 times 10 to the minus 4 meters cube. All right. All right, that's end that question. Number 5, we're almost there. Now, for number 5, A1 is to state the name of the logic gate represented by the symbol shown in figure 7. And this is a NAND gate. And just to note what a NAND gate is, it means not and. So therefore, when both are on, because the word and means both, when both inputs are on, it will not. All right, so generally AND gate, both must be on. And so this will be the opposite of AND. All right, and so it's a state the name of logic gate using the truth table shown in the table below. And so this one is a NOT gate. How we know that? Because it is opposite. So in other words, I'm not going to be like you. All right, I'm not going to be like you. So if you're 0, I'm going to be 1. Of course, if you're going to be 1, I'm going to be 0. So we're always going to be opposite. I am not you. All right. So that's an easy way kind of remember it. The names kind of suggest exactly what is happening. So again, just to point out the difference between these two, we have and. And normally means both must be on for the output to be on. And so this one is saying not and. So which means then I'm going to be opposite of the and. All right. And so the next part of the question now is that figure 8 is a digital circuit consisting of a combination of basic logic gates. And I labeled them for you so it'd be easier for you to understand. So we have 2 OR gates, we have a NOT gate, and we have a NAND gate. All right, so now you're going to see the application of this. It's a complete the truth table below for the circuit in figure 8. Now, they were we had no values in this. All the values I put them in. So first thing you have to understand here, the inputs. What you can do again to kind of understand this is just put okay, if you're on or off because one is on and zero is off, right? And so if we can say okay, let's say both of them on. Let's say one is on, one is off. Let's say the next one is off, the next one is on. Let's say both off. So that's the combination I put right there. Those are the only possibilities that we can have. All right, both on, one on, and so alternately or both off. Now the idea you want to find from C, because C is affected by A and B. Okay, so C is affected by A and B. Now, and this is for the or. So the or means you are or either. Okay, so want to understand this. Once one of them is on, the C will be on because or either or. Okay, that's what it is. So once one of you are on, if both or one of you are on, then I'm going to be on. That's a way, easy way to do it. All right, and then we're going to look at the next one we can figure out here is D, but D is affected only by B. Okay, and this is a NOT gate. NOT, which means the opposite. That means D is always opposite of B. So you have to look at B to find D. So if B is 1, D is 0. If B is 0, then D is 1. And if B is 1, then D is 0. And if B is 0, then D is 1. All right, and then now we're going to go to E. And for E, this is the NAND gate. And this is a good opportunity now for me to explain this. All right, so this is NAND, which means it's the opposite of AND. Okay? Again, E is affected by C and D. So C and D are the two inputs. So C and D are the two inputs for E. And it's again is the opposite of AND. So let's look at C and D first. So look at this carefully. So again, it will always be off when both of them are on or on, right? So therefore we have if C is on and D is off, then E will be on. Okay? But notice this now. When both of them are on, it's going to be 0, which is off. That means the only time the NAND gate is off is when both of them are on. All right? So, and mean both. You and, when you and, so when one input and the other one are on, then the output should always be off. So it's again is a not and. So just kind of remember that. All right, I hope I'm doing a good job in terms of trying for you to understand it. I'm kind of emphasizing the NAND gate because I know some people tend to be confused with that. Again, C and D, once one is on, is fine. If both of them are also off, is also fine. But the only time it will be off is when it is and. All right, and so let's look at the Z. Z is affected by C and E. Okay, so Z is affected by C and E. So you have to look at C and E, and this is an OR gate. So it could be on when either or either. And the good thing about C and E right here is that at least one of them is always on. So therefore, Z is going to be on all the time. Okay? All right. So all of that will be 1 going down. That's 6 marks right there. Again, take your time and go through it and make sure you understand the gates first before you actually look at the question. So part B is a figure 9 shows an arrangement of making an electromagnet. So this is an electromagnet right here. And this is a diagram. We have a coil of thick copper wire. We have a core electromagnet. And we have our first question here. It says state a material which is suitable for the core of electromagnet. And so it is always soft iron core that is used for electromagnet. And for part 2, it says list 2 factors which would cause an increase in the strength of an electromagnet. And this is increase the number of turns or increase the current. All right, so those are the 2 things that will definitely affect. And then part 3 is a state how component X can be used to increase the strength of an electromagnet. And component X right here, it is the resistor. And so what you can do here is to decrease the resistance. So if you have less resistance, then more current will flow. All right, so lower resistance equal to higher current flow. All right, so that's the only thing we could do right there, decrease the resistance in it. All right. If you talk about the wire, you can use thicker wires because thicker wires allow more current to flow, which is less resistance as well. All right. But they didn't ask about the wires, they asked about the resistor. All right. So for part 4, it said when the switch is closed, the reading on the ammeter is 1.5 amperes. Calculate the resistance of the circuit. And as we know this popular formula, V is equal to I times R. And so we have our V, which is 12 volts. And we have our current, which is 1.5 ampere, which is given this question. And we know the 12 volts coming from the diagram right here. That's our 12 volts. All right. Just to point it out for you. And so if you want to find resistance based on this formula, so R is going to be equal to V over I. And so V, which is 12 divided by I, which is 1.5, we get our 8 ohms. All right. And that's finished that question. Now we're on to our last question. It's a figure 10 shows a vacuum tube with a radioactive source which emits alpha particles, beta particles, and gamma ray through an electric field. All right. And here, right here at the end here, on the right, we have our radioactive source. All right. And of course, point to note, we have our positive and negative sides. That's very important to note that. All right. So part A asks us to describe the paths of the alpha particles, beta particles, and gamma ray as well, as they pass through the electric field. State a reason for each answer. So for the alpha particles, point to note again that alpha particles are positive, and look at the diagram carefully. The bottom is negative. All right, and so therefore they will attract to the negative plate and deflect downwards because on the bottom is negative. So positive attracted to negative. The particles travel towards the negative plate. They deflect towards the bottom or the negative particles. All right, so those, a combination of different points will give you 2 marks. You don't have to have everything here, but referring to the direction moving downwards, negative attract to positive or positive attract to negative. All right, for the beta particles now, the beta particles are negatively charged, and so therefore these will attract to the positive plate and deflect upwards. So the particles travel towards the positive plate, deflect towards the top or positive plate. So that red piece here, that actually will give you the solid marks. All right, and so again, while alpha particles are going downwards, beta particles are going upwards based on the charged plates. Now for the gamma rays. Now gamma rays particles are neutrally charged, so there is no charge to that. So therefore there is no attraction between the plates, and so therefore we have no deflection, and so the particles just travel straight through to the vacuum. All right, and so we have no deflection towards the top or bottom. So that's the red marks or points. Those are just to kind of give you a summary of the whole thing. All right, so you can look at them again and observe and make your notes. All right, so let's jump to the next part of the question now. So the equation below represents one nuclear fission reaction utilized in power plants. And so here we have our uranium, we have our barium, and so on. All right, so it said with masses given, so we have masses here. So the mass of U, we have that here, which is 3.9 times 3.902 times 10 to the minus 25. And then for a neutron particle right here, we have 1.675, 10 times 10 to the minus 27. And then BA is 2.289 times 10 to 27. And then we have our krypton right here, which is 1.575 times 10 to the minus 27. All right, so we have uranium, barium, and krypton, and we have our neutron. All right, and so it first thing asks us here is to calculate the total mass of particles, left side, and the product side, right side. So they actually tell us where is the reactant side and what is the product side. But of course, you should know that after the arrow, they are products, and in front of the arrow, they are the reactants. All right, and so the particles here that we're going to use on the reactant side is U and N. And so all you're going to do is add up these two masses, and you get here is 3.919 times 10 to the minus 25 kg. So all you're doing is adding the masses of U and N. All right. And then now for the products, how many products do we have here? We have 4 products. However, the gamma ray has no mass, right? So therefore, we're going to do BA, KR, and N. However, N is 3 of them. That's very important to note. You have 3 N's. So you have to multiply the N by 3. And so here we have a total of 8.889 times 10 to the minus 27 kg. And then, all right, let's go back so you can have take a snapshot of that or write that down as quickly as you possibly can. All right, so those are the two masses, the reactants, which are the particles that you use, and the products, which is the final thing we get after the reaction has taken place. Now, they ask us to find the mass difference, and so the mass difference is what you get from the product minus what you started out with, which is the reactant. So once you minus those two values, what you're going to get here is 3.83 times 10 to the minus 25 kg. Now, for part 3, it said the energy released in the nuclear reaction, given that the speed of light is c, which is c is the speed of light, 3 times 10 to the 8 meters per second. And so what here, the formula we're going to use here is E is equal to mc squared. And so therefore E here is equal to m that was given up there that we calculate. So notice the mass here, the mass difference, we're going to use that because that's the energy released. The difference between the mass, that's the energy that is released. All right. And so once you multiply that mass times the speed of light squared, then what you should get here is 3.4 times 10 to the minus 8 joules. All right, so please make sure to square the 3 times 8 to the 10. All right, I should put a bracket right here and put the square, but yep, just make sure to square that, multiply by that mass, and you get your 3.4 times 10 to the minus 8 joules. All right, and we are finished with this review. Thank you for watching, and I hope to see you soon. All right, so take care, and good luck on the examinations as well.